What's up, you scholars of enlightenment? Welcome back to another tech roundup with my friend and colleague, Dr. Ramsey Faragher. Remember, he's the real life James Bond Q, according to Top Gear magazine. So he knows everything tech, everything navigation, everything sensing. Ramsey, welcome back again. Another month gone by very quickly.
Yeah. And I became a dad in the ensuing period for the third time. So I've been very busy.
It's not really, it's not really becoming a dad, that, is it? It's the third time. Like, no, slower. It's got to be lower down.
You'd be amazed how much you forget. Yeah.
Is that purposeful that you forgot, or just?
I think it's correlated to lack of sleep with children. It definitely changes your brain in lots of ways, I'd say.
A little bit of damage there, maybe. So today we're going to be talking about a lot of very interesting things. So we're going to be talking about the backsides of black holes, as promised, Google's time crystals, and how astronomers have seen the backs of black holes, as I say. Timestamps for each of these will be in the description. But we're going to start with something a little bit closer to home for us here, Ramsey, in the UK, because last month we covered this, which was the UK ping-demic. So just to remind people of what this is, here in the UK, we have this NHS track and trace app, which uses Bluetooth to see if you've been within 5 meters. 2 meters, is it?
Within 2 meters for 15 minutes.
That's
is
right.
The rather dodgy way of deciding, but in a binary manner, you're good, you're not good.
Yes. Whether you've been within 2 meters for 15 minutes of someone who has had a positive COVID test. And this has led to a lot of problems over the last month. I think last week or the week before, 700,000 people getting pinged, and huge problems with this because people are getting pinged through the walls of their home because the Bluetooth can go through the wall. Somebody sat reading a book on the other side and they've got COVID and it thinks that you're sharing air with that person. So you get pinged as potentially having been exposed to COVID. You're sitting on the bus, you're driving past someone, you can get pinged. So we were talking last month about how this might be fixed, Ramsey. And you mentioned there's a couple of ways you could fix it. You could use the ultrasound on the phone to give a little echo, see if you're in the same room with the person, or it bounces off the wall so you're not. Clever tech ways of doing it. You could allow people who are vaccinated not to have to isolate. The government seems to have gone a very interesting, low rent way maybe of doing it. And they've simply said, we're not going to look back 5 days anymore in the app. We're going to look back 2 days. What's your thoughts on that?
That definitely means they only needed to change one line of code. So
yes,
it was quick.
There's one variable at the top, which was 5, is now 2. And then they're like, right, that'll do. Out that goes. Done.
So it's certainly confirmed that brought the numbers down. I think we saw, did the numbers drop to about half, about 40%?
I've got a link here that it went down 43%. So if you're dialing it in from 5 to 3, that would make sense. 5 to 2, so you're getting a little bit over 40%. You might have expected 60% if it was just, uniform going from 5 to 2 days. But I guess there's some sort of interaction there between weekdays and weekends, and I'm not entirely sure whether you meet more people on a weekend or during a weekday at work at the moment, given the restrictions. So, but around 50% seems to just be, we've just lost cases that are now not getting shown up because we're only looking back 2 days instead of 5. It doesn't seem that anything in terms of the pandemic or the virus has been taken care of. They've just gone, sod it. Like we'll just close the window in time.
Yeah, so not a tech solution to a tech problem at all. So this, therefore, now is a question of, from the kind of virology point, epidemiology point, other big word point, does it make sense that just a 2-day window is representative enough of whether you're likely to have kind of picked it up, or 5 days? I mean, it's don't know really. There's going to be a while before we can determine if it has an impact on the important bit, which is the number of people who are contracting coronavirus or not. The other key thing about it is just how real the numbers were, right? So we know because of how the app was designed, and that there was
so Ramsey has a bit of inside knowledge here that you're not declaring, don't you? Because you worked on this early on, or you had some of the concepts early on and talked to some of the key players. I think you're still in contact with some of them.
Yeah, I talked to Apple and Google about how it's being implemented and gave them some tips. And I also talked to the people from the NHSX team. And I did reach out to a very senior person in the NHSX team, I probably shouldn't mention, to just
We don't
to
need to
get
say
some
any names.
No, and his email's bouncing. So either he's left or his inbox is very full over all
He's
of
just
this.
thrown the table over and he's gone. This is like, no, I've had enough now. That's it.
Or he's on holiday.
One of
But
the
anyway,
two. It could be either,
one
but
of the many.
probably the former, going with
Yeah.
the Bayesian priors.
So the key thing I think is that um, I've forgotten the point I was going to make on the tech front. I think where was I before you asked me about my insight into it?
So you were saying you'd reached out to some of the senior figures over the last couple of days to work out what was going on, and you were talking.
So yeah, the key thing is that we don't really know if the numbers are real or not. What we suspect from how the app was designed, that it's Bluetooth based and how it's set up and all this stuff, we suspect that around 30% of the hits will be not correct. That you'll be told to isolate. Around 30% somebody didn't need to. Now, that 30% is the same whether they look back 5 days or 2 days, right? It'll still be that of the people that are getting told, 30% roughly don't actually need to isolate. Now, that's what we think based on how the app designed it is the case. But what you really need to do is find out the proper stats on all of those people that were told to isolate when they did a test, how many of them had it, and therefore, like, what is the actual effectiveness?
Yeah,
of the
get that temporal alignment of, which ones are the best pings? Are they 5 days ago? Are they 4 days? Are they 3 days? Rather than just hatchet jobbing off like three of them, which could be the more useful ones, right? From an epidemiological standpoint.
Yeah. I mean, there's all sorts of variables in this, but the interesting piece of data that we just don't have, that hopefully will come out over time, is of what proportion of people who are told to isolate do a test and find that they did pick it up, because that's the one of the indicators as to how effective this all is.
So it strikes me, Ramsey, that this is sort of, I don't think the UK government's going to get great props for how it's handled the pandemic, and I think this sounds like just another hatchet job of like, we've got a problem, how are we going to fix it? Just sort of hack it, because I think in 2 weeks it lapses anyway, and you don't have to isolate if you get pinged by this app anyway, if you've been vaccinated. So it strikes me as just sort of hobbling to the line at the moment. What do you make of that assessment?
It's definitely the case through all of this that there's been a lot of kind of feeding our way through it in loads of different ways, not just the contact tracing app, but the science of wearing masks and stuff has obviously been a hot topic through it all. I think the sort of important thing is that there are still things that can be done to improve it. So if we're still in this kind of scenario in a year's time, there'll be improvements in apps and the phone to do this better. I know. Or next time, we've learned a lot through this. I think one of the major things about the way they've implemented it, that's a big departure from how I and others thought it would be done at first, is that instead of just being told to isolate because there was a record that you were near somebody, the ideal situation is actually that the records of all the people you interacted with go to a human contact tracer who does the traditional process of interviewing people and finding out if you really did sit in the same cafe as that person, or if you were the other side of the wall in a different building to that person. And that is just not being done. And if that was being done, then this whole process would be way more accurate in terms of telling people whether they should isolate or not. But the number of people interacting is so great, there's just simply nowhere near enough human contact tracers to do it in that manual way that's very accurate. So we have this middle ground where we have a system that's easy to deploy, but will have a lot of false positives.
I mean, I guess they would rather be on that side than missing that. But as you say, there's going to be an awful lot of false positives, people not being able to go to work, particularly as we come out of lockdown, coming back to work. And now we've got a problem on that side, and looks like the government hasn't really thought about how to deal with it. So yeah, let's leave that one there. So the next one I wanted to chat to you about, because this is something very much in your wheelhouse, and this came out August 4th, so a couple of days ago, and it's that Amazon has reportedly gutted a huge chunk of its secretive drone delivery project. So I believe it's called, and you'll know this better than I do, it's the Prime Air Division. So like Amazon Prime, but Prime Air Division. And, they've been making a lot of news recently with their phallic-looking rockets, but they seem to have hit a snag in this other aerial-based arena. So they've laid off 100 employees at this Prime Air Division, and they've been working on drone deliveries there since 2016, but it began to fall apart in 2019. People saying it's extremely chaotic there, high churn rate of staff. And basically, it seems to have been a massive oversell on the possibility of Amazon having this essentially 30-minute package delivery to your door with a drone. So Amazon, to give you a little bit of history, they won approval from the US Federal Aviation Authority, which is the FAA, to start flying drones in around August 2020 for deliveries. And at the time, the Prime Air Vice President, David Carbon, told us that it would be an important step towards Amazon's goals of 30-minute drone delivery. And in 2013, Jeff Bezos said in an interview with CBS that he thought drones would be making deliveries by 2018. So we've obviously gone past that deadline, probably got his sights on other areas, and he's probably not happy with the FAA because I think they just turned down the fact that he's an astronaut and said he's actually not. So Bezos is not particularly happy. The dream of these deliveries by drones seems to be circling the drain. Why is that, Ramsey? If these reports of this gutting of this section are to be believed, and I believe this is just up the road from you, right, in Cambridge?
Yep.
So you might have seen the people walking out with their boxes full of stuff. Why is this dream of deliveries of packages by drone circling the drain, basically? Is it tech? Is it safety? Is it the noise of the things? Is it aerial collisions? Is it getting the legislation through? What are the big problems with this? Because I know you've done some thoughts on this.
Yes, there's definitely three parts to this story for sure. So regulatory, tech, and just the kind of corporate business managerial aspects. So it's certainly the case that Amazon Air Prime is still continuing in the States, as far as we can tell. They've just completely shuttered all of the UK work that was going on here. And apparently one of the last tasks that the poor 100 people in the offices not too far from me were given to do was to train up all of their replacements in some of the bit of the world.
Oh, that's right. But in like Central America or something, I think. It was in like, somewhere old Nicaragua or somewhere. I seem to remember reading. I'm wondering if he's taking the $2 billion that he's offered to bribe NASA with to get back ahead of Elon Musk. I'm wondering if that's the liquidation of that is just going to move the funds into, here you go, NASA. We'll go to the moon instead of Elon Musk now. I'm wondering if there's a little bit of that there. But
I think he's got so much.
He's probably got plenty of money anyway.
Totally separate off from Amazon Air Prime stuff, but yeah, certainly there could be many reasons why they shuttered the Cambridge office and the UK parts of this. From the article that came out, it looked like there were all sorts of managerial issues and problems with sort of the office not being sort of where all of the decisions were being made on the other side of the planet. And those kind of things can always cause issues about how well something's going to be run. There's the aspect that the regulations are very different in different countries. And so it might be the case that it was just looking less and less and less likely that this particular part of the world, UK and Western Europe, were going to be able to get regulatory approval for the things they want to do, whereas in other parts of the world it's more straightforward. I think in Australia there's already companies delivering stuff by drone. I know in Ireland, Republic of Ireland, there are drone deliveries in rural areas, and for many years in parts of Africa there have been things like blood bank transfer of blood rapidly by drone between hospitals and stuff like this. So
it's an interaction of the difficulty of doing it with the British or the EU laws on maybe getting this thing out as well. It's not just one or the other. It's probably a merging between those two.
Of all of these things, and certainly sort of getting around to the tech part. They are trying to solve a very hard problem, which is to deliver packages right down to the ground, so land and deliver it and then take off again, in a really difficult environment, cities and so on, where it gets very, very difficult to safely do the sense and avoid and understand exactly where you are. It's trivially easy in the middle of like the Australian outback.
I was going to say, in Africa on a plane or on the Australian outback, delivering some blood sounds fairly easy compared to bringing something to a 26th floor balcony and dropping it off.
It's very easy to say, I guarantee this thing will come down somewhere within this 50-meter radius and not hit anything on the way down. And you might have to walk 25 meters from where I said it would be, but it'll be inside this 50-meter. That's very easy. But to say I will park in your back garden, in a 1 meter by 1 meter square, coming down the side of this skyscraper here and not hitting that train that's going that way over there, all while the GPS signals are bouncing around and everything's moving and it's a bit foggy and rainy and my cameras can't see.
Well, the UK, it's always going to be rainy in the UK, so that might play a role with it as well.
Yeah, indeed. So I think they've certainly hit one of the most challenging options in the market, that type of delivery. And even just the fact that they decided that they would land and drop it off at the ground. Other companies are aiming to simply lower things down on a tether. And of course, the higher up you are yourself, the easier it is for you to be confident you're not going to hit stuff. And the higher up you are, your GPS signals don't bounce around. Whereas when you come right down to the ground, you get all sorts of issues with that and other sensors as well.
See an iPad swinging off the bottom of a drone and clonking someone on the side of the head.
The safety stuff is really important too. So there's a huge difference between lowering packages that maybe are only allowed to weigh up to 1 kilogram to be drone delivered, like lowering those on a rope, versus having a 30 kilogram drone with 4 death blades spinning at high speed, parking that in the garden next to your toddler and your terrier. So
it sounds like it would be better off for them to have, I mean, I'm just spitballing here. I'm sure they've considered this because it's a very easy solution. Seems like it'd be better to have sort of designated drop points in a particular neighborhood where, drop it there and okay, it's there in 30 minutes. You have to walk 5-10 minutes down the road to pick it up, but hey, you've got it in 30 minutes, 40 minutes now. Sorry, and you had to walk for 5 minutes. And it sounds like that would get rid of a lot of the problems.
It's the business model of wanting to nail last mile delivery. So, last meter delivery. So people will pay the £10 extra for it to arrive in 30 minutes outside that window, especially if it's a business thing you're trying to sort out quickly, as opposed to head out 15 minutes away tomorrow to get it. So it's all to do with the expediency and ease of getting something literally in your hand as you stick your hand out the window.
I'm guessing that I remember you mentioning as well, so there's obviously a tech issue, a safety issue. You talked about noise, I think, last time we spoke as well. I don't know how noisy drones are now. I'm not one of these people there's a few people around here who seem to have an obsession with drones. They're always flying them on the park over there. But they seem quite noisy as well. If you've got tons of these things going back and forward, Amazon's basically was already a massive company, but it's exploded over the pandemic with everyone sat in at home and, buying whatever DVDs, games and other things and wanting them delivered rather than going out or being able to go out to the shops. Is there an issue with, if you've got a high volume of these things flying about, great issue with noise as well?
Yeah, it's one of the issues people have cited in terms of like where you'll actually be able to level off in reality in terms of how lucrative this market is, just how many things you can have flying around. It's certainly the case that for their size, they're very noisy objects, typically quadcopter-based delivery drones. And you have this issue that if you had a large number of them flying around in a city, the noise would literally be deafening, and you're most likely going to be capping the number that are allowed in a given area above your head, and it's just not going to be like scenes in Back to the Future 2 and these sorts of things where the sky's just full of this mess of stuff flying around, until there's much more quiet ways of doing the package deliveries.
So there's probably, like you say, 3 parts of difficulty of delivering it to that last mile or last meter, as you say. So tech, regulation, and potentially some mismanagement in that particular office all seem to have come together to say that We're not going to be getting these drone deliveries anytime soon. Have you got any idea? I know you do a lot of work in sort of this general area in navigation of when we might start to see this kind of delivery. You've said we do see it in simple cases. Is there any thought of a timescale of when we might see this?
Do you mean we specifically in the UK?
In the UK or in sort of major metropolitan areas, I'm guessing.
So it's definitely that scale of exactly what we're defining as being the drone delivery. So it's totally possible from the tech side to move the parcel, do it autonomously, get within like 50 meters easily of where you really want to be dropping it off. Talking about getting below 1 meter can be more challenging, especially if you add in weather conditions and things like this. So
probably going to need some sort of, I guess, sensor fusion like the old Teslas, right? You're going to have some sort of sonar or lidar on the damn thing to make sure it doesn't clonk a building.
The challenges
or whatever it might be.
Then, and it all just starts to then stack up and destroy the business model. So the more sensors you're putting on to make it safe and work well, the heavier it gets. You need to make the thing bigger to be able to just do the lift, and you're starting to hit issues with how far you can actually transport stuff. You end up with a very, very large platform that eats a lot of energy just to do the delivery of a small box.
Yeah.
And then if you go too big and too heavy, you'll just cross over a line on the regulators like the FAA, CA, and they'll be like, no, unsafe, it's too big and heavy. And so you have this horrible situation where you're trying to make a very small, very light object carry a package, and then you can tick all the safety boxes in case it does hit someone on the head. But you've made it so small and so light that it isn't capable of doing the urban city delivery stuff. So I think to answer your question,
no time soon sounds like the answer.
The biggest delay is going to be based on regulatory aspects, quite rightly, of people waiting. Saying this isn't safe to do it in that manner, in that environment, the way you're trying to do it, because of risk management, right? It's delivering stuff in the Australian outback to one farmhouse, right? You're at risk of killing much fewer people than going in a straight line for 5 minutes across London with a 25 kilogram drone. So regulatory reasons will always be the thing keeping us from dense city drone delivery by sky.
So it sounds like no time soon seems like the prognosis. Although maybe we're gonna start getting them dropped off in Bezos's knob rocket. We'll have to see how that one goes.
I think the sorts of things when you look up and see a drone doing some kind of delivery in the coming years, it'll be in a specific environment, and it won't be B2C. It won't be a customer. It won't be one of us.
Yeah.
It'll be something like on a hospital campus layout.
Yeah.
It'll be drones moving things between rooftop buildings in hospitals. It'll be things like drones moving stuff around,
bringing the drugs in or the bandages in or whatever it might be between specific points of importance. Rather than
exactly,
I'm not saying your house isn't important, but more centralized areas of importance, a hospital, a train station, whatever it might be.
Exactly, it's so much easier for someone to effectively get a license to run a process of this drone goes in a straight line covering this kilometer between these two buildings, and it ferries blood and antibiotics, and that's all it does. And similar stories at airports or normal ports and so on, shipping, big shipping container ports. I think that's where you most likely see drones doing like a regular job.
And you can set up those sort of waypoints, can't you, so that it can follow sort of a set path, rather than you say, Doris has ordered today instead of Mike, and Doris lives 50 meters away from Mike, so it's a completely new trajectory for the drone rather than following the same path. Okay, so it looks like no time soon on the old drones, right? The main event, or a couple of main events I wanted to get into, were the black holes and the time crystals. So I think we might start with the black holes, because the time crystals probably require a little bit more I've
lost your audio, Sam.
Am I back?
You're back.
There seemed to be just a tiny little lag there. So I thought we might talk about the black holes first. Can you see those links on your pad?
Yep.
So Stanford astrophysicists have reported the first detection of light from behind a black hole. So we've essentially seen, quote unquote, the back of a black hole for the first time. So this is an extremely interesting discovery. And it basically fulfills a prediction of Einstein's theory of general relativity, with the first X-ray emissions from the far side of a black hole. So here's the paper. It was published in Nature. And essentially, scientists were observing a supermassive black hole, which is in the 1 Zwicky 1 galaxy, which is 800 million light years away from us. It's 10 million times as massive as the sun. And they were looking at it with these two telescopes, which are called NuSTAR and XMM Newton. So they were observing this supermassive black hole in the center of this galaxy, 800 million light years away. And they were observing a series of bright sputtering flares of X-rays, which were coming out from the black hole. So we can see in this diagram here, you have these.
The accretion disk.
Yes, exactly. So we have an accretion disk of material, which is falling in towards the black hole. Maybe I can play this video a little bit. So the accretion disk of material spins around the black hole. It's material that's falling into the black hole. And as it falls into the black hole, that gravitational potential energy of the material spiraling in is converted into essentially speed, kinetic energy. And kinetic energy is heat. So these things start to rub together. They get extremely, extremely hot. And they get so hot, in fact, from atoms, you get this plasma of nuclei and electrons. There's an intense magnetic field. Those electrons get spun up and they produce these bright flashes of X-ray radiation, which are known as flares or sometimes corona. And they're the brightest X-ray sources that we have in the sky. Now, this is really interesting. I mean, they're looking at a supermassive black hole, interesting in and of itself, but it's not as interesting as what else they saw, because what else they saw, if I can bring up the paper here, is they saw, let's expand this a little bit so people can see a little bit more clearly. What they saw is that when these flares sputter, a little bit time later, there was a smaller, slightly later and different coloured echo of the flares. So on the left here, you can see when the flare sputtered in the X-rays. So this is the grey band here in terms of time. And then you see these echoes later on of exactly the same, I believe it's the iron K line. So you get the same flare sort of echoed back to you a little bit later in time. And the idea behind this is that essentially the light that is flared off can either come directly to us from the flare, it can bounce off the accretion disk and come to us, or it can even bounce off the disk, wrap round the back of the black hole because of the gravitational strength of the black hole, and then come to our eyes. So you can imagine here, I've got a picture of the black hole, the accretion disk, and the corona. And if I can show you exactly what's happening. So here, Ramsey, I've got a nice little mock-up that I can draw on with my pen. So can you see that? Ramsey, can you see that?
Sorry, I was muted.
You were muted. I know the child's crying in the background. So
yeah,
the essential idea here is, if I can draw this, is that light can come directly from the corona to your telescope. That gives us the first observation of the flare in the X-rays. So you can just see the flare in the X-rays with your telescope. Or the light can be bent down towards the accretion disk. It can then bounce back up towards your telescope and you see it. And you get a reflection and echo of the same flare, or more interestingly and new in this case, the light can come down on the back side of the black hole, but it can't reflect straight to you because it would have to come through the black hole, which is not allowed because it would be absorbed in the black hole. But what can happen is the gravity of the black hole can actually wrap it all the way around the black hole and then back to our telescope. So we get all these different echoes of the same flare. We can see it straight away, we can see it bouncing back up, or we can see it bouncing off the back of the accretion disk behind the black hole and then being wrapped round the black hole back to our telescope. And this is what gives us the echoes in the data of exactly the same flare event. So if we look again, you can see the flare where it came immediately in the grey band to your telescope, and then these reflections of the same sputtering flare but occurring later in time. And they occur at slightly different energies as well, because in the intense gravity of the black hole, you get a Doppler redshift, so very strong gravitational fields change the frequency of the light, slightly change its color, quote unquote, change it to a different wavelength of X-rays. And also the black hole is spinning. So when the accretion disk absorbs these photons and pumps them back out, it has a speed either away from the Earth or rotating towards the Earth, which also gives it a movement Doppler shift. So you see these shifts in the frequency or color of the light and delay in when we see the echo. So we can be pretty certain that these are the same flare events, but just coming at us as an echo later in time, which is really cool. And Ramsey, I think you have to deal with this when you deal with GPS satellites, right? The dealing with the changes in time due to gravitational effects.
Well, yeah, I was just going to ask you or confirm with you that the reason they know it's done the lap around the back as opposed to the option of bouncing off the front is because of the right combination of extra time delay and how much it's frequency shifted.
Yes.
And that's probably
so I covered the question. Good. While you were muted, I thought I'd go ahead and answer that question for you.
But yeah, exactly the same concepts that they're using here to confirm that we've seen the back of a black hole for the very first time are very similar to the concepts that your gran uses when she navigates to Tesco using sat-nav. Yeah, so and you have to get all of this sort of physics right, or you're 300 meters wrong. There's something like 5 relativistic corrections in GPS that if you didn't do them, you'd be hundreds of meters wrong in your position fix. And it's these sorts of things that, yeah, there's slight redshift as you go through gravitational fields, and you even correct for the fact that we're in a rotating gravitational field, which you said very important when it's the gravitational field of a black hole that's rotating. That's going to be quite a significant change to the properties of the.
Yeah, so I think you have to correct it by like microseconds. This is what looks like a kilosecond. So it's a good fraction of a second anyway. So it's scaled up quite a lot compared to, I guess, what corrections do you have to do in GPS for the fact that the satellite is essentially in a weaker gravity above our heads? Is it microseconds, even nanosecond stuff?
Yeah, nanosecond level. Some of the corrections are a bit bigger, tens and hundreds of nanoseconds. But yeah, dealing with a very different kettle of fish when you're playing with a black hole. But these sorts of ideas of using very exotic objects for these sorts of purposes of kind of delay and frequency shift and stuff is all the concepts of how one day we might navigate through the stars using pulsars actually for navigation, as if they are GPS satellites. So it's interesting if they're starting to confirm that there might be interesting properties from black holes themselves, that you can start to use those as sources of information for navigation through space. But I mean, this is what we've done here. We've confirmed that the lights, because we've known about gravitational lensing for a very long time. So we know that light is bent by black holes. This is just the first time we've seen light do like a full lap and come right back around, and then made some sensing in that mechanism. Is that right?
Yeah, I believe so. So if you look back, there was a paper last year essentially using some of the same data. If you can see that. And I think they essentially saw these reverberations. They've seen the reverberations off the disc before. What they've not seen is a reverberation from the back that has been able to be dragged all the way round. I think that is new. And also the ability to be able to clearly separate out which one is which, as you were sort of alluding to. The chap, I forget his name now, it's Dan something or other, if I go up to the top of the page, Dan Wilkins, had this model of what you would expect to see from this particular spectral line if it was getting dragged around this black hole, if there were bounces off the front of the accretion disk and the back. And essentially this model that he came up with of what he would expect to see was then very similar to what we did see in the data. So we can have some good confidence that this is exactly what we're seeing. So we'd seen these bounces before, but the new thing here is something coming from behind the black hole and also being able to separate out specifically which echoes are from behind, which are from the front, which are coming straight to us. I believe that is new and an advancement, because with the pictures of a black hole, right, we've seen essentially or to some extent might have seen light from behind a black hole, but it's difficult to know which light is coming from behind, which is coming from the front, because it's all getting mixed together as it comes towards us. So it's all about being able to separate out those different sources. And I believe that's what they've been able to do in this case. So really, really, interesting paper. It's essentially like, an analogy I like to use for this thing coming round, the light being bent around the back of the black hole, is essentially like one of these, coin drop machines. You drop the coin in and it spins around the black hole. So this is the light going around the black hole, and then it flies back out the other side, flying towards our telescope. So this is essentially the idea that Einstein came up with, that a strong gravitational source like a black hole will warp space-time, just like this shape here, and the light will skirt around that black hole, zip out and come to our eye. And as you said, we've seen this in gravitational lensing, where a strong gravitational source will lens light to our eyes, allow us to see very distant galaxies and things like this. So it's not new in that sense, but it's new that we've been able to separate out the echo coming from the back of a black hole, and that's really cool. Although I will say, I was kind of hoping that it was going to say like made by Amazon or made in China on the back, something interesting, rather than it just being. I guess there's no reason why it wouldn't be symmetrical on the backside, at least across a large number of black holes. Seems sensible that it would be.
Yeah, I can't see any reason why the back would look different from the front, because what's the definition of the back?
Exactly. It doesn't make sense to have preferred directions in that sense.
And I assume that they dropped in once again that they've confirmed that Einstein's not wrong. That's the usual.
So I'm pretty sure.
Once again, we've confirmed.
If I go to this, I am absolutely certain I will be able to find. Let me see. Control find. Where's Einstein living? There he is. He's in the first line underneath. Fulfilling a prediction of Einstein's theory of general relativity, which I think we can say he's right now. Right. He's still cranking out the hits. What, like, when did he die? still coming out with the hits.
Getting on for not quite getting on for a century, but yes, well over a century since the hits came out. Exactly.
But the really cool thing about this is that essentially you can use it as a way. You can't look at these black holes directly. They're so far away. It's very difficult to see them in the sky because they're so tiny, being so far away. Obviously they're massive, but they're so far away that they appear tiny to our telescopes. But using this process, you're essentially doing almost echolocation on the state that's around a black hole. So this light is bouncing off, and it's essentially like a LiDAR, right? When it bounces off, you get some information about the properties there. So the Doppler shift can tell you how quickly it's spinning, and this kind of thing.
Yeah, exactly. I think that's most likely the exciting thing. So this guy Dan, good chat, Dan. His model that you're just describing, the parameters that have gone into that. So what Dan will be doing now is going and looking at more black holes and fitting Dan's model to the observations. There'll be parameters going into Dan's model that are the mass of the black hole, the size and speed of the accretion disk, all that stuff. So yes, now that we've got some numbers coming off a black hole of a few different measurement types, we can start to size the things up. Yeah. And get their vital statistics, which is quite cool.
Yeah, exactly. So we can
weigh a black hole.
So we can get things like the spin of the black hole from that Doppler shift that's coming around. How fast is it spinning? We can get an idea of how much material is falling into the black hole with the frequency and the intensity of these flares. Maybe some of the sizing from and mass from when it wraps around. So there's lots of things that we can do with this, and this mission is going to continue. They're moving to the Athena X-ray Observatory, which is going to be coming online with the European Space Agency X-ray Observatory Athena, which is Advanced Telescope of High Energy Astrophysics. So there's going to be a lot more coming from this. So very interesting observation, seeing the back of a black hole, kind of cool. But the more interesting thing for physics is, as sort of Ramsey says, once you're seeing light bouncing off these things, you can start to get some information about the thing that has been bounced off of, and we can get some information as to what the environment is like around a black hole, spin, material density, things like this. So that's the interesting thing going forward. And I might try and grab one of these researchers next week to have a bit more of an in-depth chat. But very, very interesting stuff. I mean, just seeing the arse end of a black hole is cool in itself, right?
If you like that sort of thing.
Exactly. Right. So good stuff. The other thing was time crystals. So time crystals.
Leaving the best till last, Sam.
Leaving the best till last because it gets a little bit can get a little bit into the weeds here with time crystals. So Ramsey, I know you've had a little look at this. So before I go into a long spiel of what I understand time crystals to be, what have you found from your Googling?
Well, I mean, it's firmly in your wheelhouse as a CERN particle physicist.
Don't be throwing this
all on you. I think so key things I think that I've picked up on this is that the interesting thing I was trying to dig into is how much of this is hype and marketing, that there's something cool.
Most of it.
That it's actually not that exciting. And I think we will visit this part of the conversation in a moment after you've introduced this exciting. But it sounds cool, doesn't it?
It does sound cool. It sounds like you're gonna have the Thanos Infinity Stones, Back to the Future, all this sort of stuff, and really it's just a crystal going like this, which we'll come on to. So maybe if I could do a little bit of an introduction for the people watching. And if you have any questions, by the way, I know there's a few people watching. Hopefully you're enjoying the stream. Remember to leave a like. If you have any questions, feel free to put them in the chat box. So maybe if I introduce time crystals a little bit. So 2 groups have now claimed that they have produced or demonstrated a genuine time crystal. So we have a preprint from some researchers at Google. And I believe we have that link somewhere here. Where are we at? So I can go back. Here we go. So we have a preprint from some researchers at Google in collaboration with physicists at Stanford, Princeton, and other universities. And they say that they have demonstrated a genuine time crystal, which seems a little bit off because it seems, looking at some of the other research, people have produced them in the past. A separate group also claimed this month that they've made a time crystal in diamond. So this is a very hot area of research, and apparently it's so interesting because they could potentially be used as the memory in quantum computing. So if we get into this a little bit, what is a time crystal? So as Ramsey suggested, there's a bit of a disconnect between the name and what the thing actually is. So it's not a way to control time or zoom through time. It's actually a novel phase of matter that physicists have strived to realize for many years, which may or may not, as we'll come on to, have some nifty applications. So if we start, Ramsey, in 3D with something we're all kind of familiar with, which is the crystal lattice here. So the idea is that a normal quote unquote crystal obeys time translation symmetry. So what that simply means is if I put a piece of quartz on the table, the laws of physics are the same yesterday, today, tomorrow. It was a piece of quartz yesterday. If I don't do anything to it, it's a piece of quartz today. If I don't do anything, it's going to be a piece of quartz tomorrow. The rules of physics are not changing with time. So I'll just have a piece of quartz. So an ordinary crystal will just sit there on your table. It has what we call time translation symmetry. But what crystals do is they break the space translational symmetry. So if we think of a melt of a crystal cooling down, it's the same in all directions. The laws of physics are the same in all directions. Doesn't matter if I throw a ball left or right. The laws of physics are going to operate the same in those directions. But when a crystal cools down, it breaks that spatial symmetry because it picks certain interesting directions or certain interesting points to make into lattice points. So these lattice points operate differently to the spaces in between. They're special in space. And we have symmetries in certain directions through a crystal. So the crystal has lower symmetry than the laws of physics which are governing it. So the laws of physics operate the same, not at a lattice point, but the crystal has spontaneously broken space translational symmetry. It has important spatial points that seem more important or different to other points, those being the lattice points. And only minimum energy equilibrium states can break symmetry like this. So the crystal is very well ordered, very low energy, and therefore it's able to do this.
That's the special thing about crystals, because glass, gases, water, fluids, liquids, you pick any random direction and it's behaving the same along any of those points. So it's one of these features that defines what a crystal is, that it has these planes and key directions.
Exactly. So even though the laws of physics are the same in all directions, the crystal chooses special directions, which you will have seen if you've ever grown some crystals. So you ever see a sodium chloride crystals growing? They don't grow out in a big sphere. They grow out in needle-like points. They pick particular directions to go. So very interesting. That's what a crystal does. We've all seen it. Now, the interesting idea that was brought up by a guy called Frank Wilczek was, could you do this with the fourth dimension, which is, of course, time? So could you invent a crystal that operates differently at very special moments in time? So can you create a material that has a particular configuration at one time, a particular configuration which is different at another time, and then return cyclically back to the initial configuration? So it goes initial configuration, new configuration, initial configuration, new configuration. Could you make a crystal that sees certain points in time as special, not just certain points in space as special? And that seems like a sensible thing to consider, because we have 4 dimensions, 3 in space and 1 in time. So this was the idea that was put forward by Frank Wilczek in 2012. He's an MIT professor. And what that would essentially mean is that these new crystals, which he called time crystals, would break time translational symmetry. So you have a piece of...
Can you just go back a sec, Sam?
Yeah, of course, yeah.
What was this chap's name again?
Frank Wilczek.
I don't... the picture's not coming up for me yet, but I was going to query, do you think he's got enough pens?
He does need more. I hadn't noticed. I hadn't noticed that, to be honest. But he does need more pens. Right. So the idea of his time crystal was that essentially it would see certain points in time as interesting or different. So you put a piece of quartz down on your table, you come back tomorrow and it's now mica. You come back the day after, it's gone back to being quartz. You come back the day after, it's gone back to being mica, and it flips between different configurations of the material. So not only now does it have special space points, it has special time points. So it operates sort of like a pendulum in a vacuum, flopping back and forward between two different configurations of material. So I think we can show that. I think I've got a nice little picture of that, where here at time 1 in the top picture, the crystal has a particular configuration. At a time later, let's call it T, it has a different configuration, and then at 2T, it's come back to the original configuration. It's going to keep slopping back and forward between those two configurations. And this was, a very interesting idea. It sort of takes the idea of a crystal and expands it to 4 dimensions, trying to bring time into the picture, but it doesn't work. Why do you think it doesn't work, Ramsey?
I actually missed a bit of what you were saying because of my bandwidth. So what were you saying? And now I've lost your audio.
Why do you think a time crystal doesn't work?
Doesn't work in the manner of flicking back between two states?
Yes.
Well, we think it does, doesn't it? Don't we?
Well, why didn't Wilczek's work?
Oh, he didn't excite it with a laser beam, probably.
Yes, right. So this can't happen in what we call thermal equilibrium. So if the thing is allowed to swap energy essentially with the environment, it settles down into one state like a normal crystal and just sits there. We don't get this slopping backwards and forwards between states. So this was a nice idea, the idea of the time crystal from Wilczek, but it didn't work. So a lot of people scratched their head. They went away and they thought, well, how on earth can we make one of these things? And what they determined was that there's actually 3 key ingredients. So I know this is a little bit heavy, but unfortunately time crystals are a little bit heavy. There's 3 key ingredients. You need to have what they call a many body localized state. Now what that means is essentially you have a few particles. Get down to this nice picture we've got. You need to have several particles, several quanta, which are trapped in a particular state. So here we have 6 particles. They have their spins. One is spin down, spin up, spin down, spin up, spin up, spin down. And you trap them in a special crystal in this state. It's called a many body localized state, and they're forced to stay in this state. But what you can do if you're very clever is you can fire a laser beam at them and get them to flip up and down using a laser beam. So you now have 2 states which have similar energy, because up and down are just something we define. 2 distinguishable states that we can flip through by just applying a laser beam to this thing. And what we see is if we try and drive this thing with a laser beam, it will flop backwards and forwards between these 2 states without taking any energy from the laser beam whatsoever. So essentially we have a clock. It flops backwards and forwards in time between these 2 states without taking any energy from the laser beam. And the really...
Did they say in the paper how they know it's not taking any energy from the laser beam? Do you know?
I didn't dive too far into the exact mechanics and the implementation of what they did. I just took that on faith.
Yeah.
So I couldn't answer that intelligently, but they're pretty sure this is the case. So yeah. The interesting thing with this is you essentially have 2 states at the same energy, which means it can move between those 2 states without requiring any energy or giving up any energy. And you essentially get this glitching between 2 states. So if we look at the sort of the picture at the top of this article, you can see it's in one of those degenerate states with the same energy, and it can just move between those 2 states. And it does so in a periodic fashion. So at t equals 0, it's on the left. T equals t, it's on the right. T equals 2t, back on the left. 3t, back on the right. And it can essentially flop between 2 states indefinitely, being driven by this laser.
Interesting and dangerous about the visual aid here, I suppose, is that what we're looking at is something spatially hopping between positions, right? Whereas that's not what goes on at all. You've got the crystal is staying perfectly still, and it's the aspect of the spin that's changing,
that's flipping up and down,
spin down. So
but
and
it doesn't look as exciting to watch that. Maybe this video is a little bit better. I've got a nice little video.
well, it's just a visual aid, right? But this is the challenge of how you get across complicated concepts like time crystals to the general public, and then what they understand thinks it means. I mean, the concept of spin, Sam, as a particle physicist, it's not easy to describe, is it? The noddy thing that is taught at noddy thing that's taught at university. Interesting wording, I suppose. The simplest way that it's put across when you taught it at university is you're imagining like literally a spinning top.
Yeah.
And it has an up and a down, and it can be spinning unstable up down, like north south on the pole of a magnet, up and down. But things with this property of spin from a quantum point of view, you can have half spin, can't you? Which means that actually it goes through 2 rotations to get back to the start.
Yeah,
so it's very difficult to imagine physically what spin is.
So the idea of spin essentially operates like angular momentum. So if you can imagine the moon going around the Earth, you have an amount of angular momentum depending on how massive the moon is and how fast it's going around the Earth. That gives it its angular momentum. And the idea of spin is usually taught to you as it's the electron. Well, the angular momentum of the electron is it whizzing around the nucleus, and then you're taught spin is kind of like if the moon was then spinning itself, right? So, or maybe a better example is the Earth going around the sun, right? It has an angular momentum, and also the Earth itself is spinning. It has a spin around its own axis. Now, we know in particle physics that that's not actually what's going on, because as far as we know, the electron is a point particle, so it can't have any sort of intrinsic spin in a classical sense. It's more just a number that we assign to the spin of the electron, and then when we assign it that number, we can do calculations that give us accurate results. So spin is an intrinsic property of the electron. As a fermion, it's a half, like you say, plus or minus a half. Rather than being anything that we can sort of take an analog for in the classical sense.
We measure spin, is it, I can't remember, is it through sensing magnetic fields?
I forget, but yes, essentially by aligning things with magnetic fields. I remember the old Stern-Gerschlach experiment and things where you put it through different magnetic fields to measure it, this kind of thing.
Split them out by the spin, exactly. So what we're kind of saying here, I think, is that you've got parts of the crystal lattice with this property that we label as spin, and it has 2 states. And for a normal crystal, you just stare at it and it remains in the same spin state.
Yeah.
But for a time crystal, it's flipping between spin states.
Yeah.
The crystal's staying still in space, but the property of parts of the crystal is oscillating backwards and forwards.
Yeah.
Supposedly without changing energy state. So the argument here is that both spin states are the lowest they can reach, and it flops between the 2 energy states.
So I mean, let's say you had 3 and it was up, up, up. Down, down, down would also be the same energy state, because it would be the same interactions between those 3 spins. Just up or down is what we define, right?
They're all aligned.
They're basically, they're all aligned. So it can switch between up and down, which have the same energy, the same interactions, but we could distinguish them, which means that we essentially see this flopping back and forward between these 2 states. And it looks like motion without energy, but it's not really motion. It's just a changing of an intrinsic property of these materials. But it's kind of cool. Now the problem is, well, actually, first of all, the really interesting thing is, the reason this is a time crystal, the reason it breaks that time translation symmetry, where there's particular interesting points in time, is because if you drive it with a laser with a frequency f, the thing actually flops back and forward between up and down, the 2 states, with a frequency that's a multiple of that frequency. So it might be twice every wobble or 3 times every wobble of the laser. So it's not in perfect sync with the laser. It seems to have to pick out special points in time itself where it wants to flip. Now, why exactly it does that, I'm not exactly sure, and I'm not sure the scientists are particularly sure either. But the point is that it breaks that time translation symmetry. It seems to have discrete points in time relative to the laser frequency that it wants to flip. Why that's the case, I'm not particularly sure. But it does satisfy the idea of there being special times where this crystal wants to do things, and therefore it fulfills this idea of being a time crystal, which cares about essentially the time on the clock when it's going to do things.
Yeah.
So, I mean, it's kind of cool. It flips back and forward. Now, why people are getting so excited about this is the idea that it could be used as memory for a quantum computer. So I guess you have two states, just like we have in a computer where we have a 1 or a 0, you have an up or a down here. You have two states. And the idea is that this could be used on a quantum level, because this is spins flipping up and down, as the memory storage device for a quantum computer. So people throw this idea out, but then when you look at the articles that people put out on this stuff, it's like, yeah, we could use this in the quantum computer. Okay, how are you going to do that? Don't really know, but
yeah,
we could.
It's the interesting thing I was looking into. I have a bit of a what should I call it? Kind of a litmus test for whether a piece of interesting new laboratory research that's done something wacky is going to have real physical uses and something that's going to change the world. Because basically, if the researchers have said that it's going to replace GPS, then it's not. And they're just looking at any other excuse to justify the research. And interestingly, when you Google applications of time crystal, people are talking about using them for GPS. So I'm not entirely certain that they have any good applications. So what they're proposing here is that time crystals might have an application in atomic clocks, and therefore have a link to GPS.
So because it has this perfectly periodic flopping back and forward between the two states, it is essentially a quantum clock, right? If I look at it at a particular time and I measure the interval it takes to flip back, I can now know that I can measure any event, right? So somebody runs from here to across the field. I know that I can measure that it took him 10 flips to run across the park, or 20 flips or 30 flips. So I can use it as a measurement unit, that flipping rate. And I believe this is what we do in atomic clocks, right? The transitions between different atoms, we define that as a particular amount of time. So it's a similar idea.
There are loads and loads of sources of oscillation that we can use as a clock. You mentioned a pendulum earlier, obviously, and there's already loads of ways that we excite atoms at the moment in atomic clocks in order to measure frequencies from them and translate the frequency into time and use that. And the most important thing to do with how good a clock is the stability of that oscillation. And that's the thing that I was trying to dig into that no one's talked about. The only way that this thing would be some kind of breakthrough for atomic clocks and therefore useful for GPS would be that the periodicity of this oscillation is unchangeably, identically, perfectly the same, whether you heat it up, cool it down, punch it in the face. And I'm being serious there. Like, if you jolt oscillators of all types, they get a bit upset, change their frequency, come back. I mean, just, smack a pendulum, right? You've disrupted the beautiful swinging motion that it was undergoing. And so you'd have to prove to me that a time crystal's flipping between two states is the most regimented source of counting that we can possibly imagine, whether it's at almost no Kelvin up 300 degrees C, or whether I'm shaking it violently, or whether I change that frequency of that laser beam that you said you used. Because if the frequency of that laser beam, if the periodicity of this thing is just 2f, and actually all you have is the stability of the laser generating that frequency. And in that case, you take the time crystal away and you use the laser's frequency.
I was going to say,
as your source. You don't need the time crystal at all.
Well, it's interesting that you should raise this point, because if you can just see the update I've put on the screen by whizzing this video on a bit. This is Fermilab's time crystal video, which has some quite nice animations in it. So give a little shout out to them rather than just stealing their things without saying. You can actually use, so you excite this flipping back and forward with a particular laser pattern. It turns out that you can actually use a laser pattern which isn't that well, which doesn't look exactly like the one that you used before, and it will still settle into this same pendulum flopping backward state. So there seems to be a certain sort of funnel which brings it into this behavior. There is a certain amount of stability.
Yeah, it's like a natural frequency, right? It sounds a bit like anything with a natural frequency can drive slightly off the frequency, and it will start to actually be excited at its frequency.
Yeah.
But still, like, it won't be perfect. It won't be perfectly on, this is where you get really down into the absolute weeds of just how perfect an oscillation needs to be outstripping our current generations of quantum clocks. So I mean, I might look into this a bit more and see, but I also don't quite follow. It was checked out there, right, that it could be used for memory in quantum computers. I think that was one suggestion. So, I mean, the way memory works is that you have two states or more maybe, and that when you put it in a certain state, it stays there, because when you want to load your photos back off your hard disk next year to look at them again, you don't want them to have been flipping backwards and forwards between pictures of you and pictures of a grapefruit. So I'm not sure the property of something that sits there flipping states is the definition of awful memory. So I don't quite follow that bit. So we'd have to understand what.
I think I would have to dig a little bit more into that to exactly understand why they think it could be used as memory. The thing that seems to come up is that it is based on quanta and it has two states. So that's sort of like a bit of computer memory. But I'm not entirely convinced. As you say, I think that's a little bit of a leap of faith.
Perhaps they're saying that because it only flips when the laser beam's turned on, you can flip the state of the time crystal with the laser beam on. And they'd have to argue that way of storing memory is kind of more space efficient, more energy efficient, something. There must be an argument that they've found something that can be flipped between two states, and it's smaller, better, cheaper than other mechanisms we use right now. So maybe they're arguing that every single atom in a crystal lattice can be individually gone and poked inside this lattice and flipped, with no other states being flipped by the laser along the way. And then you might find that you've got very, very, very dense memory. Could be that.
Yeah. I'm going to have to drag one of them on for a chat next week and roast them a little bit, because I think it seems more like a theoretical oddity at the moment rather than something we can use. The question comes up, and you sort of alluded to it a little bit there, that they need the laser on to do this at the moment. It's not just something that can sit there and do it itself. Now, I believe you can for a little bit, but then it dies away. So you need to have that laser beam there. You can't just have it going by itself. So you're still having to put energy in the form of a laser. It's just not being taken by the system. So the crystal itself, they're all getting very excited because, it seems like it evades the second law of thermodynamics because it doesn't take in any energy, and therefore the disorder in the system doesn't go up and this kind of thing. But you're just firing the energy off with the laser anyway to do something. Whether the system takes it or not, you're still having to fire a laser at the damn thing, which takes some energy. And
I don't think I've seen people writing about this second law and stuff, but the second law states that the entropy of the system either naturally, spontaneously goes up or stays the same unless you put work in to reduce it. And what the time crystal is doing is remaining in a fixed state of entropy. Yeah. So I don't think we've got any naughty violations of the second law.
No, we don't. So when they say evade, it just seems to mean is at the limit, is at the limit of what's allowed. So,
well, this is the most interesting thing for me about this whole thing.
Do you have 0, 1, 2, 3, 4, 5, 6 kids? I've got 0 kids. Ooh, you're evading having kids. It's like, it doesn't, you just at the lower limit of what's allowed. It's okay, I guess.
It's definitely the lowest energy state, having zero kids.
I am evading having kids, by the way. So I can hear you because I can hear you're screaming. But yes, so I don't think there's any naughty violations that, as you put it, that people seem to think this is particularly interesting. One you had a little bit of a whinge about this yesterday was this has been called a new state of matter. So, it's getting quite a lot of fanfare. People saying it's a new state of matter. The question is, how do you define a state of matter? So it's essentially distinguished by step changes, right, in physical properties. When we change the pressure and temperature, usually, so we get solid, liquid, gas, plasma.
Yeah.
In this case, what has changed? So it's now broken another symmetry. It's now sees important time points, so it's broken time translational symmetry. So I guess it has had a step change in how it behaves physically, and there's also a level of stability there because it seems to want to be funneled into operating this way. So much like ice can stay stable at -10 or -20 or -30 or -1, there's a level of stability there. So you can argue it is a new state of matter, and indeed they have. But I don't know, it just intrinsically it feels a little bit forced to me compared to the other states of matter that we have.
And in my opinion, it's very much like,
because it's not in equilibrium as well. It's sort of, you've got to do very special things to sort of keep it there.
I think it's akin to redefining what a planet is and kicking poor old Pluto out, right? And like, I'd say it's a phase of a crystal structure where a crystal structure is a solid state of matter. So I'd have a smaller set of states, because your Wikipedia, there's about 12 states of matter according to Wikipedia, and I'm sure some people might categorize them down into
the modern states.
Yeah. I mean, there's some well-established new. So, as you say, there were 4 for a good long time, and then Bose-Einstein condensates and fermionic condensates, and superfluidity, and a few other bits and pieces. And
I love in this how they've sort of got at the top the ones that people know from GCSE that I teach when I'm tutoring: solid, liquid, gas, vapor, plasma, and then it just goes.
Yeah. Anyone who can edit Wikipedia and add their PhD reference in gets a state of matter. Yeah, so I'd argue that there's kind of subcategories here, and I'd call the time crystal a phase of a solid, to be honest, Sam.
Yeah. So the final thing I sort of wanted to come on to on this is, why is everyone getting their knickers in a twist so much about Google coming up with this? Because it seems like people have made these time crystals, these types of time crystals, which are governed by or driven by a laser. People have made this back in 2017. There's couple of groups recently have come up with it. University of Harvard, University of Maryland. So the people at Google aren't the first. They didn't come up with the idea. Why is it that Google's getting such big fanfare on this? Is it just a good PR job? I mean, when we even looked, you sent me this one. Back in 2020, last year, the first ever observation of time crystals interacting. So you've now got more than one, and we're looking at their interaction. So it's certainly not Google coming up with this thing firsthand. So why have we got them coming out and saying first time?
From what I can tell, there's been different analogues of the time crystal concept and different ways of confirming that the properties exist. And from what I gather, this was certainly the first time someone used a quantum computer and used the qubits in the quantum computer to represent the spin elements that are flip-flop between states. And if there is really sort of an application step directly into memory of quantum computer systems, then you can see how it's kind of taking something that otherwise could just be a useless bit of physics into the direction of an application. And like I said,
so we've set it up inside. We've set up this oddity inside a quantum computing machine, which shows at least we can set it up. Whether we can use it or not is unclear. But within the framework of a quantum computer with these qubits, which are these silicon strips, these super cooled silicon strips, at least we can set up this thing, which I guess it looks more like fusing it with a quantum computer, whereas really what you're just doing is using the structure of the quantum computer to set up the old experiment. But it looks like they're more closely linked now because it's inside a quantum computer.
Yeah. And I don't think exactly what they've done, as far as I understand it, I don't think exactly what they've done is going to be the steps along the way, because qubits are the very delicate, very complicated, difficult part. So I think this is one of the most complicated quantum computers there are, and it's got like 20 qubits.
Yeah.
And so if you're using the qubits just to represent a time crystal, just to store a 1 or a 0, that is not the best use of a qubit. Go and get a solid state hard disk and have billions of.
Oh, that's true actually, because if you need to use 20 qubits just to have one of these time crystals, then you're not going to be able to represent many things. You're not going to be able to do many calculations. So that's a good point.
Yeah, exactly. So it seemed to have been that they used it as a way to kind of confirm that if you went and found another clever way of making a time crystal in such a way that you had, 1 mole of memory states in your little crystal, then we might be off to the races. But I don't think using the most complicated quantum computer on the planet to just have a very expensive oscillator swing backwards and forwards is where they're going.
So maybe we can. I always think it's very illustrative, like you said, that the comments that they've got at the bottom. These discussions will continue, driven by the possibility of exploration of quantum computers. So it's definitely not the direct application. And the one that was very telling to me, if I can find it, was a comment by this chap Moisner. I think it's in this article. Let me see if I can find it. There it is. Has we got him again? Moesner. Yes, we got 8 copies of him, and there was a really beautiful comment which illustrated that this might not be very useful. So let me see if I can find it.
Yeah, you see that paragraph you had just up there was just wrong, where he said the second law states that entropy always increases. That's not true. It's not the second law of thermodynamic states.
So here's the statement that I wanted to find anyway. So it said it's unclear whether this Floquet time crystal might have a practical use, but its stability seems promising to Moisner. Something that's as stable as this is unusual, and special things become useful, he said. So basically, at the moment, it's a little bit of an oddity. It stays very stable in terms of how well it reproduces in time, but I think the sort of upshot of that is I'm not really sure how we're going to use it, but it's kind of cool. Yeah.
And this is actually an interesting quote. While the chap doesn't know anything about the second law of thermodynamics, I agree that if the stability is crazy high, and I might try and have a little look into seeing if they've tried to measure the stability, and if the stability is unrelated to the stability of the frequency that's driving it and so on, there could be something interesting there for the atomic clock type thing. But the interesting thing for me is the first sentence, right? This guy saying, I don't think this might have practical use. Now, that reminds me of a very famous quote for me from history. So Hertz, the German physicist that discovered the radio waves, right, of whom has the unit of frequency. I think he's Heinrich Hertz from memory, but anyway, the chap is called Hertz. Right back in the late 1800s. There's a beautiful statement from him after he discovered radio electromagnetic radiation, where he said, I do not believe that these wireless radio waves which I discovered will ever have any practical use. And of course, I'm Wi-Fiing you right now and so on. And we our entire civilization at the moment kind of is built around wireless radio waves in one way or another, especially if you're ever using the internet anywhere. So it's a very interesting quote to see that. So we'll see if this chap is as not unprescient as Hertz himself was.
No, you're exactly right. So I probably gave it the negative PR treatment of he doesn't seem to know how we're going to use this. But obviously, this happens a lot in physics. We didn't know what we were going to do with quantum mechanics, and now we have computers and quantum cryptography and all sorts of interesting things. So there's also, I mean, which is basically the sentiment of his statement, because it's unusual. It's not unusual that we don't know what to do with it yet, but maybe some uses for it will come along down the road. So
time will tell.
Time will indeed tell. So it's not as exciting, as interesting as maybe some of the hype. They definitely got a great PR company on the old time crystal. Because
I mean, if this thing was called the Florian State, no one would care.
Yeah, or if they said it's basically
State,
a pendulum in a vacuum, like people would have been like,
this is a bit like those things that spin around in space and keep going.
Yeah, and one side is black and one side is white, and it's got two states, and it just keeps spinning around. But because it's quantum, everyone is like, so. Yes. Maybe useful in the future, maybe not. But that's time crystals. Very, very interesting, and we'll see what comes of that. If anything more comes out of that, we will be sure to let you know. Ramsey, those are the main topics I've come up with this month, and most of them from this week, of interesting tech and sciencey stuff. Anything else leap out at you before we call it a day? If anyone's got any questions, by the way. Thank you for staying with us through discussing these really interesting topics. If anyone's got any questions, feel free to put them in the chat box, and we'll answer them. Otherwise, we'll probably finish in the next few minutes. Anything else jumped out at you, Ramsey, over the last month?
Yeah, I thought instead of looking like a rabbit in the headlights this time when you asked me that, I would plan something.
I did. I do catch you with this one usually.
Yeah,
because this is like my power play at the end of each session. I'm like,
I know.
He's not done his homework. Like, what's going on?
Exactly, getting your own back for all those years. So I have
Ramsey was my lab supervisor, by the way, and I thought I'd done a good report. My first lab that I ever did in Cambridge, and I thought I'd done a really good report, and it comes back with like 1 out of 4, like shit, basically. With more red pen than I think I've ever seen, and probably had to get a second red pen.
See me on it.
See me.
I don't often write "see me" on people's work. But anyway, to answer your original question, Google announced, I think it was yesterday, that they're going to be using an in-house chip, a tensor chip, as they've called it, in their upcoming smartphones.
Let's get this up so people can see. Google Pixel chip.
What's cool about this, and I'm sure there'll be more bits and pieces coming out of it over the coming weeks and months, is that
this one.
Let's see. It'll be called the tensor chip. Yeah.
This one.
So most smartphones today have an ARM chip, some architecture from the company here in Cambridge called ARM, and that's what they base all the compute of the phone around. Google have clearly been working on this for a while. They've got their own architecture chip, which is going to be, I'm pretty sure, going to be geared around being very efficient at doing neural network type tasks and what everyone colloquially calls AI. They will have developed a chip that is very power efficient at doing exactly the sorts of maths that neural networks do. And neural networks today power all sorts of aspects of like speech recognition on your phone, recognizing objects in the scene. All sorts of things are going to start moving towards neural networks, which are artificial brains. So basically, Google have designed this little chip that does a better job of giving you lots of little artificial brains inside your phone than the traditional architecture chips are. And it's a really interesting
Skynet, mate. It's a learning computer. We're going to get Skyneted, aren't we?
It's a more battery efficient way of doing
destroying the entire human race.
So It's not going to become sentient and take over like those. That was the plot of one of the Terminator films, wasn't it?
That is the whole plot of the Terminator film.
Yeah. Well, I just mean when they like retconned it, so that it was like.
Oh yes, when they retconned it, it was. Didn't they make it like a social media platform?
Yeah.
Yeah,
Exactly.
that was
Yeah.
awful. That film.
But yeah, so the tensor chip, I'm sure we'll hear more of it as time goes on, and other companies will move in the same direction. There are already companies that are trying to make neural processors, as they call them, which have an architecture focused towards this new type of way of processing data. So we'll see more of this as time goes on.
Do we have a simple level of this already? Because with things like predictive text, or is that just frequency based type thing?
So the sort of category of machine learning and artificial intelligence, there are lots of different algorithms or methodologies to do things like decide what word comes next, given some words you've seen, or convert the voltage pattern that is currently being generated on that microphone there by my air compressions hitting it, converting those voltages into sentences and words. Those sorts of methodologies of doing that clever stuff are all in the branches of machine learning, and neural networks is just one of these types of machine learning algorithm. But if you design your chips specifically with neural nets in mind, they have to be efficient. They need to be different from the standard CPUs that we use in all of our current technologies. And these neural processors that people talk about now instead of central processing units have just an architecture that lends itself to neural networks. If you like, we could dive into this a little bit next time.
Yeah,
I could explain what that is.
That sounds really interesting. So we'll get into that next time. I think we're going to also, just to sort of tee this up a little bit, next week, I think if we can find the time, we should be able to find the time. We're going to have a look into some of the most famous UFO or UAP sightings. So Ramsey has set up a nice little sort of trap for me, where he's gonna make me watch 3 of the most famous UAP or UFOs colloquially sightings that people have essentially. I think they're Navy personnel or
U.S. Navy officially released videos of
yes,
unidentified aerial phenomena that have caused all sorts of interesting things.
And tell the people what you're going to make me do.
Well, we're going to sit down as scientists and look at these interesting.
I'm going to sit down as a guinea pig
and discuss what we think might be going on in them. Yeah.
Right. So Ramsey's going to essentially ask me what I think's going on. I've committed to not looking at these things. I haven't seen them yet.
I've lost all your audio. I don't know if it was just for me, but it's just classic talking about aliens and all your audio goes.
Am I back now? Did I get cut off?
Back now. Yeah.
So Ramsey's gonna check if I know what's going on, and he's gonna cheat because he knows the answers already, and I'll probably look like a fool, but at least we'll be able to understand why people find these things so convincing.
If I literally knew exactly what was on those videos, I probably would not be allowed to talk about it. But we can just we can discuss what's the most.
That's true. If we get it right, you'll just hear like a single gunshot, and the stream will go blank, and that'll be that.
That's not a joke. Yeah.
Be careful.
Anyway,
so that's coming along next week. Ramsey, I've really enjoyed it as usual. Anything else before we finish off?
No.
We've had a good set of concurrent viewers, but no questions. So either the explanations were very good or absolutely awful. One of the two.
We were probably oscillating between both states.
There we go.
Without needing to be excited by a laser.
Quantum superposition of excellent explanation and the topic being incredibly difficult to ask questions on. We'll go with that. Right, Ramsey, thank you so much for taking the time again. Lots of interesting stuff seems to be coming up, so that should be good to go next month. And let's have this chat about UAPs next week. Have a good weekend, buddy.
Cheers, you too, Sam. Bye, everybody.
Yeah, bye, everyone. Thank you very much for stopping by. Really good to have you If you enjoyed this, remember to leave a like, subscribe, comment. I'd love to hear your comments down below about these fascinating topics, and share the video more widely if you enjoyed it, because that really, really helps me out and I would really, really appreciate it. So thanks a lot, guys, and see you again soon.